We'll have our first talk by Brian Welch. Brian, would you like to share your screen?
Yep, here it goes.
Thank you. And Brian will be talking to us about Relics, Parsec-Scale star clusters observed in the first billion years.
All right, thank you. Yep, I'm Brian Welch. I am a PhD student at Johns Hopkins, and I'm going to be talking about some superlative lensed galaxies that we found in the Relics survey, including one that is magnified enough to see Parsec-Scale star clusters at redshift greater than 6. So first, a little background on Relics. Relics was a 188 orbit Hubble program that was targeting 41 massive galaxy clusters with the goal of looking for some of the best and brightest high redshift lensed galaxies that we could find. So by looking at a wide area, the goal is to be able to pick out sort of the most interesting objects that we could find with Hubble. We also had over 1,000 hours of Spitzer, which really helps with some of these higher redshift galaxies to make sure that we know that they are real high redshift galaxies as opposed to lower redshift interlopers. And I'll talk a little bit more about that in a bit. But first, just quickly, why we like gravitational lensing for some of these studies. The big reason is that it magnifies these distant galaxies and gives us much better spatial resolution than we could hope for with current or even next generation space telescopes. So this is a lens galaxy at redshift about 2.5. And you can see the source reconstruction here has all these small clumps of stars that are on scales of a few tens of parsecs each. And then when you take this back to HST or even JWST resolution, you lose a lot of that information. You lose a lot of these little details. So if we really want to study how these galaxies are forming, we really need lensing to give us this resolution boost so that we can see down to scales similar to what we can see in local galaxies to study star formation across the board in some of these objects. I also just quickly want to show this slide from Dan Koh's talk earlier this week, just comparing the sizes to scale of some of these lensed galaxies that we're going to be looking at. Besides these two that hopefully you can see my mouse here, which do not have James Webb time, all of these are going to be targets of James Webb observations. But what I wanted to point out here is just sort of a size comparison of some of these galaxies. So for example, this is the longest lensed arc at redshift 6 that I'm going to be talking about in detail in this talk. And you can see on this slide already just how much larger this appears than some of these smaller, more point source like redshift 6 galaxies. And just how much more resolution we're going to be able to get, spatial resolution we can get with these lensed objects. So to jump into this one in particular, this is a 15 arc second long lensed arc that we've named the Sunrise Arc. It is the most highly magnified galaxy at a redshift of 6. Overall, this galaxy is magnified by about a factor of 300. So you can see in this figure on the right, this red line here is the lensing critical curve. It crosses the arc twice, so we're seeing a total of 3 multiple images of this galaxy. And especially in this middle segment here, the critical curve runs almost parallel to the arc image that we see. So we're really getting really high magnifications across the board here, giving us a lot of great details into this galaxy structure. So to actually get at all of the substructure that we see in this galaxy, I've been using a forward model technique where I create a model of the galaxy in the source plane, and then run that through our lens model to create this image plane reconstruction that you see on the left. And with this, we're able to identify a total of 7 individual star-forming clumps that really span the breadth of this galaxy. So you can see clumps 3 and 4 here form sort of a tight core at the center of this galaxy. And then we have our clump labeled clump number 1 all the way out to almost 500 parsecs from the center. And the radius of this galaxy is about 200 parsecs. So we're really seeing, the entire width of the galaxy from the very center all the way out to the edges. And this is going to help us in the future with determining, how this galaxy really formed once we get some spectroscopic data, which I'm going to talk about a little bit at the end. But this is really going to help us to figure out, if this galaxy is sort of accreting more star-forming clumps from outside, or if it's forming most of its stars from the center or inside out. So this is going to be a great opportunity to study this in the future with James Webb, to get a sense of how this is really coming together. The other interesting Redshift 6 galaxy that I want to highlight here is this one. This is the brightest Redshift 6 lensed galaxy. So its AB magnitude is about 23. It's magnified by a factor of about 20. So this just seems like a particularly interesting sort of extreme case, where obviously this one clump here is significantly brighter than anything else we've seen. So it's a very interesting object to keep looking at. So just to compare these to some other lensed clumps, I just want to point out here, this is the clump number 1 from the Sunrise arc, which is the one we have the best radius constraint on so far. The radius is less than 6 parsecs here. It's still unresolved in HST, so we can only set that upper limit, but it's already the smallest lensed clump at Redshift 6 that we found, and it's getting down to scales that we previously could only really look at lower redshifts, and even scales that we could look at in the Milky Way and other local galaxies. So now we're able to do that at much higher redshift, which is very exciting, and very exciting to continue following up. And then also the bright clump that I just showed on the previous slide is obviously significantly brighter than anything else of similar size. So it seems like a pretty extreme object. We don't have too many details about it right now, but it seems like it might be going through some sort of burst of star formation. So it's going to be, again, a very interesting object to follow up with James Webb in the future. The last arc that I want to highlight here is this lensed arc at Redshift 10. This is one that Victoria Straight mentioned in her talk yesterday as well. She's done great work with Spitzer to really pin down the redshift of this and kind of break the degeneracy with a lower redshift SED. So this is a very solid Redshift 10 galaxy at this point. And again, this one is, it's the only lensed arc at Redshift 10, so it gives us the best spatial resolution of any galaxy at this high of a redshift. So we can put our forward model to use here again. And you can see in this plot, I'm showing the actual HST data on the left side, and then the right is our forward model reconstruction. And what really shines out here is that we have 3 substructures within this galaxy. So 3 clumps that we can study. These are all pretty preliminary fits, but this is something that I am continuing to work on. And if we add these to that plot I showed earlier, you can see the radii that we get for each of these are just below 100 parsecs. And one interesting thing is that these seem to be brighter than similar sized clumps at lower redshift, implying a potentially increased star formation rate for an object of similar size, so higher star formation rate density, which is something, again, that we're going to want to follow up spectroscopically with James Webb. So this is another great target to continue looking at in the future. So I just want to end here with our vision for the future. We have one program for these galaxies that's been accepted for James Webb Cycle 1, and that's on the Sunrise arc. So we're going to be getting near-cam imaging to hopefully resolve all of these clumps and set not just upper limits, but get actual radius measurements for all of these. And then the other thing that I'm very excited about is we're going to use the near-spec MSA to put slits on each of these clumps. So we're going to be able to get spectra, which will give us solid star formation rates. It'll give us metallicities. And like I was saying before, it'll give us these things across the width of the galaxy. So we can see, if there are any metallicity gradients across this galaxy. We can see where the higher star formation rates are, and really sort of deconstruct, how this galaxy seems to be forming, and what's going on there at this galaxy in the Epoch of Reionization. So I'll leave you with that. It's a very exciting time. I'm very excited for James Webb and to get my hands on some of this data. So I'll stop there and take any questions.
All right, thank you so much, Brian. Give it just a little bit of time for people to type any questions they have in the Slack under session 4B.
Okay. How did you determine the redshift of the sunrise arc?
So right now it's just photometrically. So let's see if I can go back to a previous slide here. So it's just photometrically. We do an SED fit to the HST data, and the best fit that we get is redshift of about 6.2. Since we have this steep drop off here below the Lyman break, it's a solid redshift 6 galaxy, but we don't have a spec Z for it yet.
Next question. How much of the upper limit for the sunrise arc clump 1 of less than 6 parsecs can be changed by the uncertainties from the math model and the redshift?
So the redshift, photometrically, we're pretty solid on that. So that we don't expect to change too much. The mass model is a little bit more uncertain. So this cluster really only has a few multiple images that we can use to pin down the reconstruction, the lens model reconstruction. So I don't have an exact number, but I would say, maybe a factor of a couple. I think we have a couple different lens models, and the largest sizes are maybe slightly more than 10 parsecs, but I would have to double check those exact numbers. But yes, the mass model is a little bit uncertain right now, and this is something that we are, again, hoping to get pinned down a little bit more with our web data if we can get a few more multiple images.
Great. There's a question about whether you've considered ALMA observations of this sort.
We have. So we actually considered putting in an ALMA proposal for the last cycle, but we decided to hold off since we are going for James Webb. We're hoping that Webb will give us the spec Z for this, so then we can sort of optimize our ALMA observations a little bit more, as opposed to scanning across to try to get what the redshift is. So the plan is, once we have a spec Z, we will target this with ALMA and try to get a lot more spectroscopic information there.
Great. All right. Well, thank you. And if there are any other questions, please type them in Slack, and Brian can check that later.